I thought you might like to have some more problems to practice on, so I'm posting these. I gave it to first hour, 7th hour. I forgot to give you this piece of paper except for Rachel. But you don't really need a piece of paper because here it is. So you just try the problems and pause me and listen to what I have to say after you've given it a shot. So you're combining oxygen and methane, so you're going to have CH4 and oxygen. Of course, this is a hydrocarbon. When you burn a hydrocarbon, you get carbon dioxide and water. You may not have known that methane is CH4. Now you do. This is the chemical reaction that you use in your kitchen range if you have a gas range, and it's also the reaction that you use to keep your house warm in the wintertime. Natural gas is primarily methane. To balance the equation, you have to put a 2 and a 2 there. All right, to find moles, we're going to take, we have to find moles of each reactant to find out what's limiting. So we have 89.6 liters of oxygen. But the tricky thing about that is normally you just think, well, I got that many liters of oxygen, so I would just change that to moles by using a 22.4. But you can't do that here. Can you tell me why you cannot do this? The answer lies in that this is only true at standard conditions, and the 89.6 is not at standard conditions. So we can't do that. So I'll get rid of all this. So to find moles, instead of using the 22.4, let's use the PV equals nRT. All right, so PV equals nRT. And we know that we have 89.6 liters. That would be our volume. I'm going to put units in once on this problem, but after that I'm not going to because of space. Here this is 103 kilopascals. That's our pressure. Don't have to subtract water vapor because it doesn't say anything about water vapor. N is the number of moles, and we don't know that. That's what we're trying to find. R is the constant. We would use 8.31 since our pressure's in kilopascals, and the units on that are liter kilopascals per mole Kelvin. Then our temperature would be 298. So 298 K, because I have to change C to K. All right, just looking at unit cancellation, see K's cancel. When you divide kilopascals and liters, they're going to cancel. Whoops. So liters and kilopascals cancel. And all you're going to be left with is moles, which is what you want. So to actually do the math, I'm going to multiply my 103. I'm going to do this on the side. You won't be able to see this. So 103 times 89.6. Then I'm going to divide that answer by 8.31 and then divide it again by 298. So it turns out the number of moles of oxygen is 3.72. I'm going to write that above the O2. So I've got 3.72 moles. To find the moles of methane, we have 48 grams of methane. So you just change it to moles using standard old techniques. One mole is how many grams? 16. 48 divided by 16 is 3. So we have 3 moles of methane. So I'll write it over here, 3 moles. So then the question becomes which one runs out first. So you can tell that the oxygen is going to run out first because you would need twice as much oxygen as you have methane, and you do not have twice as much oxygen as methane. But just to show you that on paper, just take your 3 moles of methane, methane on the bottom, oxygen on the top. There's 2 moles of oxygen for every 1 mole of methane. So you would need 6 moles of oxygen. Do you have 6 moles of oxygen? Oops, didn't need to do that. Do you have 6 moles of oxygen? The answer is no. You got 3.72 moles. So this is what you have. This is what you, no, I take it back, sorry. This is what you need, and this is what you have. All right, so you don't have as much as you need, therefore the oxygen limits, so O2. Okay, the volume of excess reactant that remains when the reaction stops will be based on the oxygen. No, it would be based on a limiting reactant, yeah, which is the oxygen. So you're going to take your moles of oxygen, which is 3.72 moles, and then find out how many moles of methane you will actually use. So the number of moles of methane would be oxygen on the bottom. You have methane on the, methane on the top. It's a 1-to-2 ratio, so 1 mole for every 2 moles. So 3.72 divided by 2 is 1.36, I believe. Oops. No, 1.8, sorry, it's 1.886. So 3.72 divided by 2. So you have 1.86 moles of CH4 that you're going to use. How many moles of CH4 did you have originally? You had 3 of them. So you have 3 moles minus 1.86. And that gives us 1.14 moles excess. So now can you multiply that by 22.4 and find the volume? And the answer to that, of course, is no. The reason you can't do that is because this the lab is at 25. So if you're going to try and multiply by 22.4 liters per mole, that's wrong. You can't do it because, because the lab is not at standard conditions. All right, so what we're going to have to do is use PV equals nRT, or I mean, you could use the 22.4 and then change from standard to lab using the V1, V2 approach. But since I don't have room for that, I'm going to go with the shorter version, which is PV equals nRT. And I know N is 1.14. The pressure is lab pressure of 103. The volume,
have a good weekend.
Thank you, good night. So the volume is, we don't know. We're looking for that, so V, sorry. R is a constant. Since this is in kilopascals, I'm going to use the kilopascal constant again. And the temperature is 298. All right, so now I'm going ahead and solving for V. I'm going to do it over here. You're going to multiply these 3 together and divide by 103. So here we go, 1.14 multiplied by 8.31 multiplied by 298, then divide that answer by 103, and I get 27.4. So 27.4 would be the volume that is left over, 27.4 liters. So this is 27.4. Now if we took the products that were collected and converted to standard conditions, what would be the volume of the greenhouse gas? So you take your limiting reactant, what was that again? Oxygen. So you take your how much was it? 3.72 moles of oxygen. Whoops. 3.72 moles of oxygen. And then you would find the moles of CO2, because that's the greenhouse gas, carbon dioxide. So you'd put moles of oxygen on the bottom, moles of CO2 on the top, and that's a 1-to-2 ratio. And then you want to find the volume of that gas. So can you use this 22.4? Yes, because it says you're converting it to standard conditions. So since it says standard conditions, then we can use the 22.4 liters per mole. So 3.72 times 22.4, then divided by 2 equals 41.7. So 41.7 liters. All right, I'm going to pause this movie here, and then I'll do the other 2 problems in a separate movie. There are 3 problems on this problem set, just little review activity.